Hello and welcome to this video about Git LFS and how we deep dive into it. Today I'm going to cover the following topics. First of all, let's dive a bit into the Git internals, then see at when and why Git LFS is important, how Git LFS works with pointers and how it works for itself, and then a bit of a guide to the migration to Git LFS. And finally, I'll also do a demo. Cool. So let's dive into Git LFS. How data is stored into Git. Git is an content addressable file system. So it's a file system that contains objects with content, and Git is able to address these objects as a database, so to say. So it's an object database. In the end, it's basically a key value store, but you have different object types, so to say, so that are stored in the database, with the key being a hash and the value being the object. Now you have three kinds of objects, as I said. So you have a tree object. A tree object is in fact a list of other objects. So that can contain a blob, which is the actual content, or other trees. And other trees can then again contain blobs. And the third type you have, that's a commit object, and I'll come back to that later on. There's always one root tree object, and that's the start of everything. So the root file system, so to say, comparable with in Linux, you have the slash of your file system. That's also the root, but within a Git repository, you also have this root tree. Then blob objects are typically compressed with zlib, so that they take less storage. Then let's look at how this third commit object comes into play. So a commit object is a special object that contains a pointer to a tree object. And this tree object then is sort of the head of a branch or something like that. It's mostly a branch, and that tree object again contains either files or other tree objects. So you can say that a commit points to the root directory of a point in time of that repository. Now you see a lot of things happening here. So commit 1 references tree 1, which contains this sample file, and then you have commit 2, which points to his ancestor, which is commit 1. So a commit object contains not only a tree object, but also a pointer back to his predecessor. And commit 2 contains a tree with another new file and a version 1 of the README file. Then the third commit contains another tree with version 2 of the README file that was committed first, and the same new file that was in the previous commit as well. And it also contains some pointer to tree 1 that contains this sample RB. So this sample RB has moved into a separate folder, so to say, which then is a tree object. And to optimize, Git will simply point to that tree object again. So it's not creating more objects, it's keeping reference to existing objects as much as possible. So this is how files are stored. A lot of optimization. Git tries to make sure that no duplicates exist, so it can reference all the objects back again. Awesome. Let's move on a little bit. So commits point, as I said, to the root tree object, which contain a list of objects, and these objects are typically loose objects, so they are stored as a whole. So there is no optimization between version 1 here and version 2 there. To optimize that, Git will store these loose objects, these separate objects, into a binary pack file, and in this binary pack file it will store only the differences between the versions. So the original version is stored as a whole, and then any addition, it will only store the diffs. And that pack file is then a binary file, which is even more compact and smaller. That is all there to reduce not only storage, but also to make access to all these files and differences easier. It's not just a storage optimization, but also a performance optimization. Now let's look at how Git handles large files. So Git in Git LFS is not a GitLab thing. It's separate from GitLab. And yeah, Git handles binary files the same way as it handles normal other files. It's simply a blob, in this case with binary data. The only thing is that with binary data, Git cannot create diffs. It cannot compare these files because it cannot compare bits and bytes. It's binary. It's very difficult to make comparison between them. So it cannot do any storage optimizations for binaries. That means that if you add a binary and you add a new version of the same binary, then the entire new binary is added to your repository. Also, there's no way to view diffs between binaries, so the advantage of having multiple versions of the same binary in Git is very limited, because you cannot really see what's being changed. You can only see that the file is changed and by whom. Yeah, that's the disadvantage of why you probably should not want to store binary files in Git. To fix that problem, Git introduced a large file storage system. It's a separate sort of add-on onto Git, which installs certain Git hooks. And as I said, it's completely separate from GitLab. Only that GitLab supports Git LFS on the server as well. So if you want to use Git LFS, you do that in certain situations. So as I said, it's an extension to Git, but which can be run both locally and remotely, and it replaces binary blobs with pointers. So instead of storing the entire binary, it will store instead a small pointer, and then it will take the binary and move that to a separate storage location. So if you add binaries, then your repository is not growing so fast. So it will only keep the pointers, and you can have a lot of pointers without a lot of data, and it will then take only the LFS objects that are required. That means that if you want to clone a repository and you have like 10 versions of a large file, your clone time will be extremely slow. With Git LFS, that time is reduced a lot. And then when you clone, it will look at the pointer and it will only fetch the latest binaries when needed. Having said that, there are also reasons why you wouldn't store large binaries in Git. So for example, if you have a build that produces an artifact, for example a jar file in Java, you don't want to store jar files in the Git repository. Either build artifacts or build dependencies. So the jar files or any other files that are depending on needed to build your project, you should either fetch them or push them to an artifact repository rather than keep them in Git. In these artifact repositories, you can version them, so you'll grab a certain version out of it, and you update locally in your repository only a text file that points to a certain version. Not only build artifacts, but also, for example, AI models you should store in such a repository, or Docker images, RPM packages or Debian package or whatever package manager you have. You would also store them somewhere remote in a registry, and also Helm charts, the same thing. So anything that is sort of deployment related. It's a result of your build that should store in a registry, not a repository. I see with a registry. That's a mistake I put here. Git LFS therefore is more likely to store, for example, images or logos that you use in a website, or maybe fonts. Sometimes also audio files or video files, although for those there can be content delivery networks or corporate content storage where you would store those. But these are typically not files that are stored in a versioned registry, and mostly kept, if you want to do some version history, kept in a Git repo. So these are the typical use cases you see. Although even then, I wouldn't recommend storing very large files in Git anyway. Cool, let's move on. Now, as I said, how is Git storing this file? So if you have the same commits, but you have now a binary file, then Git stores only a pointer blob. That's a very small blob item that contains a string. So the blob becomes a text file again, and the text file is comparable. You can store diffs, etc. And the actual binary content is moved to an external storage. Now, what does it do for your repository? So let's look at an example. Let's say you have a repository and you add a binary file that's 3 megabytes. Then your repository will become 3 megabytes in size larger. If you change that binary and you make it a bit smaller, like 2.5 megabytes, then your repository will be growing with another 2.5 megabytes. Because Git will not only contain the latest version, but also any previous versions. If you change that binary again, that image again, to let's say 2.8 megabytes, then your repository again grows with another 2.8 megabytes. If you then add a large video, same thing happens. Your repository will grow with another, like in this case, 80 megabytes. So you can imagine what it does to your clone time if you have to clone all this data and all this history even with you. If you would remove those binaries and use Git LFS, then if you add a binary, then the additional repository size is 132 bytes. It's the size of the pointer. Even if you change the file, then another 132 bytes are being added. And no matter how large your files are, the additional repository size is always this 132 bytes. So one pointer, so to say, a string of characters that is added to your file, and the actual content is stored somewhere else. Now, where is this content then stored? Now let's have a look. So Git stores the LFS data, so the large file objects, in locally it can store it in your internal .git repository, for your repository directory. But you can also move it somewhere else outside of your .git repository. I will show you that in the demo. But on our GitLab server, there is also this LFS hooks installed in Gitly. So if you enable Git LFS on your project in GitLab, then these LFS hooks are installed on the Gitly server. So if you push data to Git, these LFS hooks will kick in, and it will store a pointer in your Git repository, which is the Gitly storage, and move the binary files to a separate LFS server. So if you then fetch the data again, you pull it, then you first will pull all the repository data, including the pointers, and then through these webhooks, Git will fetch LFS content and then send the binary files separately. And important notice here, if you do a git pull over SSH, then you will get your repository data over SSH, and in a second request via HTTPS, it will pull or retrieve the binary files from the LFS server. So LFS data always comes over HTTPS and not over SSH. Sorry, that's a very important thing to notice. Now, how do you start tracking files with Git LFS then? You can start this locally. So simply clone a sample Git repository. Once you have that repository, you will want to define where to store your LFS storage. The default is .git/LFS, but you can also point it to somewhere else. Now, once you have defined the storage, or you keep the default, then you have to install Git LFS. And this Git LFS install will create some webhooks, some pre-commit hooks in your Git repository to fetch any binaries and store them in the LFS storage. Then you say to LFS, okay, let's track a certain file. Now in this case, I'll track all the PNG files, all the PNG images. You can also track files by size, or there's different filters that you can use. In this case, I'll simply do all the PNGs. And that will, so this Git LFS track will create a file that's called Git attributes. It's a hidden file, .git attributes. And this .git attributes will store all the configuration for your Git LFS. Now in this case, I will add the .git attributes and my PNG file that I've added to the commit status, commit stage, and then I commit. So both the Git attributes as well as the binary files are now committed into the repository, and then you can push them to the server. On the server, if you push it to GitLab, then you have to enable Git LFS also on your repository in order to make sure that GitLab is separating the content from the repository. Now, how you do that? You go into your project settings, and under your visibility, project features and permissions, you can enable or disable Git LFS. Also, in your repository settings, you can view which projects or which files are in LFS. So in this case, you see that this image has this LFS label. So that means this is stored in LFS. And then if you dive deeper, you can also see a breakdown of, okay, this is the repository data, 10 megabytes in this case, and this is the LFS data, which is also 10 megabytes, and total is then 20 megabytes. So here you can see what's stored where. Adding new files to LFS. So again, let's start with a sample. But once you have installed Git LFS on your repository and created this Git attributes file, then you can simply start copying in a file. So take an image.png from the temp directory, I add it, and with the hooks installed, with everything prepared, you can now simply commit, and that will automatically add the image.png to the LFS storage. When you clone a repository, you don't necessarily have to get the LFS files immediately. So it can also be that with the Git clone you only get the pointers, and then you can later on do a Git LFS fetch, and this will then fetch the actual data from the LFS server. And there's also more commands in this Git LFS where Git LFS sort of re-implements commands like push and fetch and clone to make sure that also LFS data is fetched. Look at the Git LFS documentation, which is under the Git projects. Now, let's have a bit of a look on how to handle binary files with diffs and so on. As I mentioned, if you have an image and you do a diff in Git, then it will only say it's a binary file, and yeah, there's a difference between them. You don't know what. That's always the case. So that's also the reason why storing binary files in Git has not too much sense. But with Git LFS, what you can also do is you can lock files, and file locking means that, okay, you can't see the diff, so you can't also do any how is it called again? So if you want to merge and you have diffs, then you need to resolve merge conflicts. Now, that's not possible with binary files, so you therefore want to lock them sometimes. Now, if you lock them, then you prevent pushes to those files, and you protect files against simultaneous changes. So you can lock the file in GitLab or in Git locally, and then make your modifications. And once you're done, you unlock them again, and then others can modify them again. This is something that I think some people might know this from very old version control systems. They had the same thing. But with Git LFS, it's very nice to do this because you then make sure that no one else is making modifications that you cannot merge. How do you do that now? You configure locally the LFS URL. This could be gitlab.com, for example, and then you say, okay, git LFS lock, and this will push that to the LFS server URL, where then the image is locked, and then once you're done, you unlock it again, and you can continue. This can also be done inside of the of the GitLab UI. So if you have this image, you see it's LFS stored on the label, and then you can click on the lock here, which will lock the file, and then unlock to unlock it again. Now, to see which logs you have, you can go to type in git LFS logs, which will retrieve all the logs from the LFS server, or you can go into your repository and find any logged files in there, and then you can also unlock them there. Now, that's about file locking. I think it's important to be aware of this when you start using Git LFS, but if you have very static image files, then you probably won't use it a lot. Okay, when you want to start migrating an existing repository with existing data to Git LFS, you have to be careful and be aware of a few things. So let's give you a sort of a high-level migration guide. Now, step one, I've created these steps as a guideline. There's a lot of to say for each and every step. I'm not an expert, so yeah, please look at the internet how to do this best. But just to give you a few things, you first have to prepare. So you have to know in your repository which files should be stored in Git LFS, and now you have to define certain filters, which is the Git attributes, what I mentioned earlier, and you have to configure that and start adding these files. And you have to be aware that you also have to prepare things in GitLab. So in GitLab, if you want to start using Git LFS, first of all, you have to enable it on the project level. But before you can do anything, you have to unprotect any branches. And that's important. It is only temporary, but once you want to migrate to Git LFS and want to replace any existing binaries into LFS objects, that will mean it will rewrite the history, and you cannot force push to a protected branch. Allow to force push is here usually then enabled. Therefore, you have to at least uncheck that or unprotect the branch entirely to make sure that you can push and that you also can force push. And you might want to lock your repository, because if you migrate to LFS, then your entire, and then I also mean your entire Git history will be rewritten with new hashes. So everyone has to then reuse and reclone the repository and remove their old copy. Now, a very simple basic step, clone your repo, and then do Git LFS migrate. With the info, you can see what's happening. You can see what Git LFS would migrate if you do this. Then you say include any PNGs, for example, and then everything, so on every branch and history. Now this will show you what will happen, and then after that the import will actually do that. And after you are done, all these image objects are replaced, but you still have to forcefully push data to Git, because as I said, your entire history is rewritten. All of your objects have a new hash because all of the binary files have been replaced with a pointer, and therefore their content changed, and therefore that's the nature of Git. An object has an ID, and that ID is based on the actual content of that object. It's a hash. If you change the content of the object, the hash will change. With Git LFS, you will change the content of any binary object into the pointer, and therefore the hash will change, and therefore the tree object will change, and therefore the entire commit object will change. If you then force push and someone else clones it, you need to merge. That's not possible. If they have already some changes in their local repository, they can't push it anymore. So there's a potential risk of data loss there. So you have to communicate it properly. You have to make sure that people are aware of this. And yeah, maybe it's even a good idea to, before you go into this, to create a copy of your project on the server to make sure you always have an older one, of a newer one, and then do the migration there. Cool. Let's dive a bit into a demo. Now, first of all, let's look at a repository. So I have a repository that's called Git LFS, and I also have a repository that's called Git without LFS. Now here you see this label which I mentioned before. So this image file is stored in Git LFS, and the README of course isn't. Here is this Git attributes file that I mentioned, where you can see that the JPEG file is stored and filtered by LFS. So any JPEG file that's entered will be picked up by LFS and therefore moved somewhere else. Now let's look at how this looks like in Git. So here you see I'm in the Git LFS directory. If I open this, you see here the JPEG file, which is now about 3 megabytes in size. If I show you the size of the Git repository, you see that the Git repository only is 132 kilobytes. So it's very small compared to this image file. And that's because that image file is stored in Git LFS. Now, I can with Git do very raw commands to look at objects, actual objects. I'll look at the tree object that is the root of the main branch, and I would like to see the contents of it. Now I see the main tree object contains 3 files: the Git attributes, the image, and README. And these are all blobs, and these are the hashes of each of these blobs. So I can look into the hash of the image blob, and I can see that the size of that is indeed 132 bytes only. And if I look inside of it, then you can see that that size contains simply a hash to a object somewhere in the storage. You can see it's starting with 0086. So if I look at the storage, Then you see this 00 over here. Wacht. 00. This has again this 68, and that has then the entire pointer, entire hash of this this pointer, and that is then the actual blob. I can do a size of this one. Oh, but that's also working with this. And here you see that's indeed the same as here. So it's stored in the LFS storage. I have stored that here. So here you can see LFS storage is in the documents development and an LFS storage, and therefore it's stored separate from my repository. So let's create a new branch. And then I will copy a file, the same image file that I had previously, but now a separate version of it. So here you see now I have an image file that's not 3 but 7 megabytes. If I add this image file, then you see it's modified. If I now commit, now it's added. If I look at the size of the Git repository, you see it's now just a tiny little bit larger, 156K. Not super much, not very much. If I look at the commit object, so I can get the log, the latest commit, which is this one. I can again open this file. You see that this commit object contains a tree object and a parent, and that's the previous commit, so to say, but also the author and the committer and the message that I put in. If I now look into this tree object, and here you see the image again. Now, if I again look into this object, then you see that here now the image has a new hash, and the size is now a lot larger. So not 3 but 7. But the repository size, as you just saw, it didn't really change. So the repository size is a little bit larger, but not a lot. But the image is indeed double in size. So that's why you want to store images not in Git, but somewhere else. As you also saw, is that I just added a file and then committed it, and if I push it now, then it will be picked up by GitLab and will be stored in LFS as well. So I can simply work with normal commands as once I installed Git LFS, and the Git hooks will pick up everything for me. So if I would do the same thing for without LFS, then you have an entirely different story. So here you see again the same file, Git in the Git repository. If I show you the size of this one, you see it's 3 megabytes. If I now do create a new branch, And again, I will copy the file. You see now the file is again 7 megabytes. I can add it. Git commit. If I now look at the repository size, it's 10 megabytes. So it's the 7 megabytes of this file are added to the existing 3. So it's more than double in size. And that's, yeah, again, the reason why you want to do that. Also, if I look at the first of all, look inside of it. I now cannot really look into the blobs because let me go into the commit first. Cut file. Then we'll take the tree object that we then have to view, and here have this one. So I should only do -s here, because you will see that this is 7.5 megabytes long, that's large in size, and if I do a min-p, then I would get all the binary data of that file, and my terminal does not like that. Yeah, so that's it. In terms of migration, yeah, I can also show you here on this one what will happen if I do a Git LFS migrate info. As you see, it will go through my repository and will look at everything, and I see, okay, I have a JPEG file of 11 megabytes, and that's something, and there's 2 copies of it, which you could then move to LFS. You could also, it will list you anything. You can create filters here, so I can say don't do just everything, but filter on JPEG files, and then it will only show me the JPEG files. And this is a way to get information about your repository and which files you want to move to LFS. But there is also different tools that you can use to also remove any historical files, because this usually only migrates all the existing ones in the branches and in the main to LFS, but all the history that have been stored previously are kept, and you can also remove those from your repository. But that's a little bit more complicated, and therefore there's quite a few tools that you can use if you want to do that. Yeah, contact me and I can link you to few documents if you want to. Cool. Then with that, thanks for watching. Thanks, and if you have any questions, please drop me a message.